In this video session, we are going to write a recursive function to search an element in a sorted list using binary search algorithm. So the prerequisite for binary search algorithm is that we must be having a sorted list in which we can find an element. So here in this program, what we are going to do is we are going to write a recursive function which should return the index of the position at which the search element was found, and if it is not found in the sorted list, then it would return -1. So that is our goal. And before writing the function, let us first discuss about binary search algorithm a little bit, and then we'll go for writing the code. So let me take you to my notes. So here is a sorted list: 2, 4, 10, 15, 21, 25, 36. So binary search is applied this way, that we would be comparing the search element. Let's say the search element is 10, and we would compare the search element with the middle position, the element at the middle position of the array. So here the middle position is this, that is third index is the middle position, and the element at middle position is 15. So we would compare the search element, whatever it might be. So in this case we have 10 with the middle element, and if it is equal, that is the search element is found at the middle position, then the position of the middle element would be returned, would be the answer, right? And if it is not found at the middle position, then we'll have to compare the search element with the middle element, and if the search element is greater than the middle element, then we can be sure that it would never be found on the left hand side, because it is already greater than the middle element. Let's say if the search element is say 25, then we would have a condition that the search element is greater than the middle element. Then we are sure that the search element would never be found on the left hand side, because all the elements on the left hand side are still lesser than the middle element, and the search element is found to be greater than the middle element. So we can neglect the left hand side list, and then we can apply the search of this element on the right hand side of the list. So starting from one position on the right hand side of the middle element up to the last position, this would be our next list on which we would be searching the search element, the element that we are searching for, right? So we would apply the binary search again on this list. Fine. And in the cases where the search element is lesser than the middle element, like in this case if you are searching for 10, so it is lesser than 15, so our search would be applied on the list that is on the left hand side of the middle element. And here we would apply again the binary search algorithm. The left hand side list is sorted, and then we would compare the search element with the middle element of the list, and if it is equal, then we are going to return back the position of the middle element, and if it is not equal, then again we would compare that whether it is greater than or lesser than. If it is lesser than, again this of this list, whichever is the left hand side list, on that the search would be performed. If it is greater, then it would be performed on the list which is on the right hand side of the middle element. So this is the algorithm. And what would be the base case of this algorithm? So if you see that a binary search problem is can be divided into smaller problems of binary search. Like in this case, that we applied binary search on this list which is of size 7, and then if the element is not found, if the search element is not found at the middle position, then we are breaking it down into smaller binary search problem based on the condition whether the search element is greater than the middle element or lesser than the middle element. So if it is greater, then our new problem would be this one, in which we would apply binary search. So this list would be our sub problem on which we would be applying the binary search, right? So this would be our sub problem, and if it is lesser than, then this would become the list on which we would apply the binary search. So these are smaller problems of binary search, and the solution of the smaller problems is giving us the solution of the actual problem, right? So this is a recursive algorithm, and what would be the base case of the recursive algorithm is that if the list size is 0, right? So that would be the base case. If list size is 0, then the search element cannot be found in the list, and we are going to return a -1, right? Now to put this into code, we'll have to define the range of the indexes in which we are going to apply the search. So our actual problem would have a lower index and an upper index, right? And so we are going to first of all find the middle position. So middle position's formula would be like this, excuse me. So middle elements formula would be like this: mid equals to lower plus upper divided by 2, then a floor. So what does the floor operator means? Floor operator, if lower plus upper divided by 2 comes out to be a fractional number, then the floor operator would get us the element which is highest amongst the get us the integer which is highest among all the integers lesser than the fractional number, right? So if this lower plus upper, so let us apply it. Lower here is 0 and upper here is 6. So 0 plus 6 divided by 2 is 3, right? And floor of 3 is nothing but 3 itself. Had there been 8 elements in the list, so the lower would be 0 and then upper would have been 7. So 0 plus 7 divided by 2 is 3.5, and floor of it would be 3. Why? Because 3 is the highest integer amongst all the integers which are lesser than 3.5, and that is the definition of floor. Fine. So we would compare the element at this position. So in this case we have lower plus upper divided by 2 is equals to 3. So third position is of that of 15, so 10 would be compared with 15, right? And now as 10 is lesser than 15, it is not found here, and it is lesser than 15, so our next binary search should be applied here. So in this case, if this is middle position, so the binary search, the next binary search problem would be applied on lower same as the actual problem and upper equals to mid -1. So here the upper would be actually mid -1, right, which is one position on the left of the middle position. So let us write the code and we will discuss it there on the ID. So we are writing a recursive function for binary search, and it is supposed to return us the position of the search element if it is found, and if it is not found, then it is going to return us -1. In any case, it is going to return an integer value, so the return type would be int. Now let us name it as binary search, and then this function is going to take as parameter the array in which it is supposed to search the element, and this array as a prerequisite should be a sorted list, otherwise binary search cannot be applied. Now the element that has to be searched, so let us name it as key, and the lower and upper index, lower and upper index on which, between which the search has to be done. So in the initial problem, the lower index would be 0 and upper index would be the last index of the sorted list. Like here, the lower index would be 0 position and upper index would be 0, 1, 2, 3, 4, 5, 6. 6 would be the upper, right? And in the sub problems, this lower and upper could differ. So we would see that. Now the base case is where there is no element, there are no elements in the list. When there are no elements in the list, then we would have a condition where lower would surpass the upper. So when lower becomes greater than upper, then we know that there are no elements in the list, and the search is a failure, and in that case we are going to return -1. Now if lower is lesser than or equals to upper, then there are elements in the list, and then we'll have to compare the key with the middle element. So first of all we would find the middle position, and middle position can be found by the formula mid equals to lower plus upper divided by 2. So this has to be put into bracket, lower plus upper divided by 2, and as it is an integer division, so it would always find the floor of the division. So integer division would always find floor. So any floor or ceiling, anything can be taken, that would be no problem, that would make no difference in binary search. So here we are taking the floor of it. Now we have the middle position, so the binary search algorithm says that we'll have to compare it with the element at the middle position, and if it is equal, that means if the key value is found at the middle position, so it is given by the array is ARR, and at the middle position we have this element ARR mid, and if it is equal, then we are going to return mid, that is the position at which the element was found, and if it is not equal, then we are going to see if the key value is greater than middle position or not, greater than the middle element or not. If it is greater than middle element, then we are going to apply binary search on the list at the right hand side of the middle position. So return, again we are going to apply a binary search and on the same array for the same key value, but now the range would be different and it would be mid plus 1. So the lower index of the new binary search would be mid plus 1 because it is the list on the right hand side of the middle element, and the upper index would be same as its parent problem. And if these two conditions are filled, that means key element is lesser than the middle element. In that case we are going to apply the binary search on the left hand side list. So the left hand side list would be, the indexes of it would be lower to mid minus 1, right? So these would be our sub problems. Depending upon this condition, one of the sub problems would be chosen, right? And whatever the solution of the sub problem is, that would itself be the solution of the actual problem. So whatever is returned by binary search or applied on the left hand side or right hand side list, that would be returned back by the actual problem to the function which has called this binary search. So with that, we have completed our code of binary search. So it is as simple as that. If you understood it, the algorithm, then the code is nothing but just the replica of whatever we have understood on our notes page. Now let us apply some test cases on this function and see if it is working fine. So let me print the position of binary search on ARR, comma, let's say the key value is 10, and lower, as I said, the initial problem would be having a lower index as 0 and the upper index would be the position of the last element. So here the last element is at position 6, 0, 1, 2, 3, 4, 5, 6. So the last position would be 6. Now it should return us, it should give us the position of element 10, that is 2. So let us run and if it is, and check whether it is giving us correct. So it is giving a value 2. Now let us check the position 25. So 25's index is 5. So it is giving 5, so it is correct. Let us check for the test case where the element does not exist. So let's say 5, right? So this does not exist in the list, so it should return -1. So it is -1. So our binary search implementation is working perfectly fine. So with that, we have completed the coding of binary search algorithm. Hope you have enjoyed this video. I'd keep on uploading such videos, so keep watching these videos. Hope you are enjoying them, and keep liking my videos so that I remain motivated to upload such videos over and over again. Thank you. Thanks for watching.